So the next memory allocation directive, Word, is also allocating 16-bit integers in memory. And it's structured such as, it basically says, let's take 3 duplications of the question mark, which linker will initialize to 0. All uninitialized data is initialized to 0. So basically what we do is we say that we want this duplication of question mark is 3 duplications of question mark, but each of these question marks is the word size. So basically what it gives us is 2-byte size integers like this, 3 of them. Okay, so 3 2-byte size integers that we have right here in those parentheses in this section. And then we say that let's duplicate them 5 times. So this gets duplicated 5 times, 3 times, 4 times, 5 times. Okay, so each time we fill the same information in these, and so altogether this becomes like a structure like this, and altogether all of this is allocated as a single block. Okay, so 5, 1, 2, 3, 4, 5 repetitions of 1, 2, 3 16-bit size integers, and the question mark is used to indicate perhaps that we don't really care what the value is, but the linker, because this is constant data segment, it's another part of the global data segment, which is just simply contains constant data, will set them all to zeros. Okay, so let's take a look at the same information inside the listing file. So array 2 here corresponds to the beginning of constant segment memory plus 67 bytes, and this tells us that okay, you have this 5 repetitions of 3 2-byte integers just like this. So this is what's happening as a result of this. All right, so this brings us over to offset 61, at which we have another example of an array available in assembler. So here now we use 32-bit integers, which is double word. So if word is 16-bit, then double word is 32-bit, and we store integers right here, simply a sequence of integers at this address, and the integers are storing 1, 2, 3, and 4. But look how the listing shows the difference between 16-bit storage and 32-bit storage. So this is all hexadecimal expression of all 32 bits filled with zeros and 1, and then 2, 3, 4 are subsequent integers. So this is what the listing file explains to us with respect to us allocating memory. Now another example of an array is using byte again, right? So using bytes, but this time we use single quoted literal character initializer, right? So the digits are 1, 2, 3, 4, 5 through 7, and then comma 0. So of course what's going to be stored right here is going to be the encodings of individual character digits, rather, right, as characters. And so this 1, 2, 3, 4, 5, so forth becomes 31, 32, 33, 35, and 36, 37, 38, and this byte, right, so this last byte in this allocation, we simply initialize it to 0. So when we're using string literals in assembly, we can use both single quotes and double quotes. It works the same way, but they're not automatically 0 terminated as we used to in C and C++. So instead of automatically being 0 terminated, you have to do this manually. So if we wanted to make this a 0 terminated plain text string like traditional C type of string, we need to add 0 manually. So this sort of like demonstrates this type of work. So altogether this will be 9 bytes, right? 1 through 8 plus 0, 9 bytes. Okay, and also byte array just with decimal values. This time it's 10 integers like this. And again, this is just shown right here that it stores individual bytes with the values corresponding to decimal values 10, 20, and so forth, and 100. 100 decimal is 64 hexadecimal, so that's pretty consistent. And so this is just a longer story of what gets allocated in this data allocation directives using duplications or sequences of values at specific labels. And we call them arrays, but that's ways to initialize arrays in assembler. And then we can apply length of to a byte, so byte 1. Obviously you see this, and we can apply length of. So length of should return 3 elements. Okay, so length of really measures how many of these bytes, words, or double words ended up being generated by this memory allocation directive at each specific label. Okay, so basically the operator is asking you what is your label, and I will be able to find out for you how much stuff is being stored over there as a result of these memory allocation directives. So of course 3 elements right here, so it prints 3. A length of array 1 should be, and here you see that we get hexadecimal indications of what X is being assigned. So 32 is hexadecimal 20. Okay, so the listing file shows the final assignment of this X, which we use just to be able to accept the value of length of in our demonstration. So this is not an executable code. It just simply at assembler, when assembler runs through the source code and allocates our constant memory segment, it also is capable of computing these things for us. And so hopefully we get we get good answers to what we already been trying to examine manually through these allocations. So array 2 size, which is the length of operator, returned as 5 times 3, so it should be 15. And here array 2 15 is hexadecimal F. Okay, so this becomes 15. Array 3 is of course 4 elements, so right here array 3, length of array 3 is 4. Okay, and then digit string is 9 digits altogether, and our byte array, another byte array, is 10. Now the size of multiplies the length of result by the size of byte, size of word, or double word. So byte is 1 byte in size, word is 2 bytes in size, and the double word is 4 bytes in size. So this is why it's just basically the same set of values multiplied by 1, by 2, by 4, and by 1. Okay, so we get these results, and so that's what gets computed by size of. The size of this memory in bytes, or the size of this memory in bytes. And finally, type is just simply, it's not, it doesn't care about what's being allocated. It simply tells us what is the size of byte. So size of a byte is 1, size of a word right here is 2 bytes, and size of array 3, which is double word, is 4 byte size. So this is like how big each one of these integers is in computer memory, right? So these are very useful three very useful operators alongside with constants such as equality directive that creates a constant, and this is the running constant redefinition. It's rather not a constant, it's just like a assembly type variable that we change in order to be able to visualize the result in the listing file.